Okay, in this series we'll be looking at the laws of logarithms, and by definition the logarithm of a number, say n, to a base written as log of b for instance, is the power to which the base must be raised to get that number. That is, if we have log n to the base of b, we are saying that the answer will be that value to which this base b must be raised to before you have n. So let's label it as x. So if you have log 1000 for instance to the base of 10, you are simply asked to find what is that number that 10 must be raised to for you to get 1000, and the answer is 3, because 10 raised to the power of 3 is equal to 1000. Therefore, we said the log of 1000 to the base of 10 is equal to 3. So with this, there are certain laws that govern the operations of logarithm. Now, basically, we have logarithm expressed to the base of 10. And when we have a logarithm expressed in the base of 10, we call that natural logarithm. And we have other bases as well where logarithm can be expressed in, like base 2, base 5, base 8, like you do have it in number-based system. Though the natural form or the natural base in which logarithms are expressed is in the base of 10. So one of the laws we have in logarithm is the addition law. The number one law, we have the addition law. And what is this law all about? When two logarithms of same base are added, the result is usually the product of the logarithms to their common base. That's what addition law is all about. For instance, if you have log 4 to base 10 added to log 250 to base of 10, what this addition law says is that you should find the product of these numbers to their common base. That is, log 10 is their common base, so we're going to multiply 4 by 250, and that will give us log 10. 4 times 250 is 1000, and log 1000 to the base of 10, it's equal to 3, because 3 is a number to which 10 must be raised to give this 1000. The second law is known as the subtraction law. We have the subtraction law. Again, when two logarithms of the same base are subtracted, the one being subtracted is used to divide the other, and all of them must be expressed in their common base. For example, when we have log 100 to the base of 5 minus log 4 to base of 5, we have to divide 100 by 4. That is what this subtraction law is all about. The same base, that is log 100 over 4 expressed in base of 5. So this is equal to log 25 to the base of 5. Log 25 to base of 5 can be expressed further as log 5 raised to the power of 2 to base 5. And this is equal to, this is another law. We are going to see it in the next law of logarithm. When you have a power like this, you are going to multiply it by the log itself. So we have 2 log 5 to the base of 5. And a log to itself, that is another law again that we are already touching. When you have log 5 to base 5, the answer is 1. So that we are going to have 2 multiplied by 1 equal to 2. That's how to solve this kind of problem using subtraction law. The third law is the power law. We have the power law. And what does this law emphasize? When a logarithm is raised to a certain power, the power is used to multiply the logarithm itself. That is what we did here a while ago. When a logarithm is raised to a certain power, the power is used to multiply the logarithm itself. Example, if we have log x to the power of m in base b, this is same as saying m, which is a power here, multiplying the log itself. The log here is log x to the base of b. So what you have here is the same with what you have there. Anytime you have a log of a number raised to a certain power, use that power and multiply the log itself, and the result is same. So let's use number to also do that. We have log 9 to the power of 3 to base 3, and that's equal to, we are going to use this power to multiply the log itself. So we have 3 log 9 to base 3, and this is equal to, remember 9 can be reduced further, so we are going to have 3 log 3 raised to power 2 then base 3, because 3 raised to power 2 will give us this 9 back. Again, we have another power here, so we are going to bring this power back to this place, and we will have 3 times 2 log 3 to base of 3. So that we have 3 times 2 giving us 6. Log 3 to base 3. Log 3 to base 3, we have 1. Finally, 6 times 1 is equal to 6. So log 9 raised to power 3 to base 3 is equal to 6. The next law that we'll be looking at is the power of the base. We have power of the base. Now, for this law of logarithm, when the base is the one that has the power, the reciprocal of this power is used to multiply the logarithm itself. When the base is the one that has the power, the reciprocal of this power is used to multiply the logarithm itself. Example, if we have log 16 in base 2 and this base has power of 3, what that implies is we are to use the reciprocal of this power and multiply the log itself. That is, the reciprocal of 3 is going to be 1 over 3. So we use it to multiply the log 16 to base 2. Remember when we are looking at power law? For power law, it is the number that has the power. So we'll pick this power direct and multiply by the log. But in this case, it is the base that has the power and not the number. So when the base is the one having the power, we have to use the reciprocal of this power to multiply the log. So that is all about this. So this is equal to 1 over 3 log 16 to base 2 can be rewritten as log 2 raised to the power of 4, because 2 times 2 times 2 in 4 places will give us 16, and that is equal to, we have now a power is here, that is power of 4. Based on this power law, we are going to bring that 4 and multiply by what we have here, so that we'll have 4 times 1 over 3 log 2 base 2, right? 4 times 1 over 3 log 2 to base 2, it's equal to 4 times 1 over 3 is 4 over 3. Then log 2 to base 2 is 1, because a log to its base is 1. So multiplying this by 1, we are still having 4 over 3. So that is the fourth law of logarithm. The next one that we'll be looking at is logarithm to its own base. Now, according to this law, the log of a number to its base is equal to 1. For instance, if you have log a to base a, the result will be 1. If you have log 10 to base 10, the result will be 1. If you have log 2 to base 2, the result will be 1. So anytime you are given a problem and you come across this stage in the process of solving that problem where you have a log to its base, just know that the answer is 1. The next law we'll be looking at is logarithm of 1. The logarithm of 1 to any given base at all is equal to 0. For instance, if you have log 1 to base 10, the answer is equal to 0. If you have log 1 to base 3, the answer is also equal to 0. No matter the base you are dealing with, provided it is log of 1, it's equal to 0. For us to prove this, if log 1, for instance, to base 10, let's say is equal to x, we want to prove that this x is actually equal to 0. And for us to do that, remember that the logarithm of a number, say n, is the power to which the base must be raised to give that number. So this is 1, right? That is log of 1. For us to get this 1, it is the value to which this 10, which is a base in this case, must be raised to give this 1. And for us to do that, it implies that 10 raised to the power of x is equal to 1. Remember, from indices, we have what's called a zero index, where any number raised to power 0 is equal to 1, right? It's already established from indices that 10 raised to power 0, for instance, is equal to 1. 20, 1,000, 1 million, or whatever number at all you can think about raised to the power of 0 is equal to 1. So it implies that for us to have this expression in such a way that the bases are the same, so that we can equate their power, we are going to replace this 1 with 10 raised to the power of 0, so that we have 10 raised to the power of x equal to 10 raised to the power 0, since 10 raised to the power 0 is the same thing as 1. From this, since the bases are the same, from indices we can equate their powers. It then means that x is equal to 0. That's how to prove that the logarithm of a number to any given base is actually equal to 0. The next law of logarithm that we'll be considering now is we have the reciprocal law. For this law, when the reciprocal of a logarithm is required, the base and the number are interchanged. That is, their positions are interchanged. For instance, if you are asked to find log 8 to base 2, the reciprocal of this, if you ask to find the reciprocal of log 8 to base 2, you are going to have 1 over log 2 to base 8. That's all about this reciprocal law. We are going to prove that to be sure that truly log 8 to base 2 is the same thing as 1 over log 2 to base 8. Right? So this is a reciprocal. And when you are dealing with reciprocal, again, I said the base and the number are interchanged. Their positions are interchanged. You can see in this case, it is log of 8. The base is 2. But once it is reciprocal, it is changing to log of 2, base of 8. So let's prove that this and this are actually equal. So if we are to find log 8, as a way of proving this, log 8 to base 2 is going to be equal to, remember, log 8 to base 2 is going to be, what number are we going to raise 2, which is the base here too, before we can get this 8, right? So let's say that number is x. So log 8 to base 2 is equal to x. You know, we can reduce 8 further. So we have log 8 to base 2. It's same thing as saying log 2 raised to the power of 3 to base 2. Right? And this is equal to, from our power law, we are going to multiply this power by the log itself so that it becomes 3 log 2 to base 2. And you know, from the previous, one of the previous laws we've looked at, that is a logarithm to its own base. We have log 2 to base 2 here, so we are going to equate it to 1. That is 3 multiplied by 1, and that's equal to 3. So it means the logarithm of 8 to base 2 is equal to 3. That is, 3 is that number that 2 must be raised to give. So this x in this case is equal to 3. Because 2 raised to power 3, that's 2 times 2 times 2 in 3 places is equal to 8. Implying that the log of 8 to base 2 is equal to 3. Right? Now let's prove that when we look for 1 over log 2 to base 8, we are also going to have 3. Right? Now, when you have this, 1 over log 2 to base 8, this is equal to 1 over 1 over 3. How do we get this 1 over 1 over 3? We are going to prove it below here. For instance, let's leave this numerator alone and treat log 2 to base 8. Now, if you have log 2 to base 8, let's say that's equal to x. We want to know which number will 8 be raised to so that we can get this 2. If we have this, it means 8 raised to the power of x is equal to 2. From this now, we need to express this in the same base so that we can equate their powers. 8 raised to power x is the same thing as 2 raised to the power of 3x. And this is equal to 2 here raised to the power of 1. Right? Now that their bases are the same, we can equate their powers. And equating their powers here, we have 3x equal to 1. For us to get the value of x, we'll divide both sides by 3, implying that x here is equal to 1 over 3. So that is why 1 over log 2 to base 8 here is equal to 1 divided by 1 over 3. So let's continue with the solution to see if we will also get 3 like we did have here. So 1 over 1 over 3, reciprocating this, we are going to have 1 multiplied by 3 will go up, while 1 will come down. And this is 1 times 3 giving us 3, divide by this one, and it's equal to 3. So you can see that the reciprocal law holds for this, such that if you are asked to find the reciprocal of a logarithm, you should now exchange the position of the base and that of the number, and you discover from this proof that the result will be same in each case. See that log 8 base 2 here is equal to 3, and 1 over log 2 to base 8 here is also equal to 3.